Guys, we're back with an episode of Site Visit here in Needham, and today we're going to be addressing a structural walkthrough. So we're going to walk through the entire building and walk through the basement, all of the first floor, second floor framing, and the roof framing. And to do that, I got Rens from Hazel Neal. How are you,
Nice
man?
to be here.
So we're going to walk through this whole home. You guys did the structural design on it. Before we get into the specifics, what's your goal with a structural walkthrough?
Yeah, so on a high-end custom home, it's pretty common for the building inspector to want a sign-off from the structural engineer. So when we collaborate with a team like NS Builders, we have shop drawing review, we're looking at mix design, the rebar in the foundation, the wood framing, the beams. We're really communicating throughout the process, and so today is the final walkthrough before we issue our letter to the building department saying they've built everything to our design intent, right? We issue design drawings, they're not construction drawings. They're building off from our design intent, so it's important to have that line of communication and then final walkthrough to make sure we're all on the same page.
And I think to expand on that, oftentimes, we talked about this a little off camera, but oftentimes people will just go through the whole process and then call you and ask you to come sign off on it. And it can't work like that. It's a collaborative effort.
Yes.
And my team, as well as your team, they've been working through this project from foundation all the way to roof, walking through all specific details, beam changes, any change that had happened in the field, alternates. So you guys are well versed. This is, like you said, a final kind of blessing before we close these walls up.
Yeah. We're very familiar with what you've built before we ever showed up. And the rub he's talking about, in commercial, controlled construction means that it's like a documented process on how we're involved in construction. In residential building code, it's not quite as spelled out. So sometimes people can go build the house off our drawings having never talked to us, and then they're saying, hey, the building inspector asked us for a letter, and they're coming to ask us to come out, and they might have drywall up, and they'll be like, can you sign off on the house? And it's like, we haven't had any visibility. So the fact that we're communicating along the entire build puts everybody in a good position.
Cool. I'm gonna grab Mike, and then we'll walk through this place and we'll get through it.
Let's do it.
Cool. So when you're walking like a residential basement, what are you looking for?
Residential basement, I mean, the thing I'm going to be looking for is like top of wall bracing. How basement walls are braced is they're pinned by the slab and they're pinned by the floor framing. So I'm looking to see that, like, we have attachment, there's a sill on it in that direction. On this direction, I'm looking for the blocking.
The perpendicular
blocking?
blocking?
The perpendicular blocking. So even in this case, this is the type of thing in traditional house framing, like, will get missed a lot.
Yeah.
I've actually heard a framer tell me the strapping for the ceiling and the jip is what like pins the bottom of that like gable wall. Yeah, the jip.
Maybe the subfloor.
The subfloor could work.
So what are these blocking? This blocking doing really?
That's stiffening up the end bay, right? So this wall is pushing the soils on the outside of this foundation wall, and it wants to push it over. So that floor is bracing the top of the foundation wall, but the joists run parallel to the wall. So that's an unstable mechanism that we're trying to push load through. So that blocking ties that all together so that it's pushing on the diaphragm as a unit, because that's all nailed from the top.
Yeah, got it.
That same thing happens upstairs on the gable walls where the joists aren't framing into the exterior wall.
Sure.
That's what we're doing.
One of the things I remember our foundation guy, he was like, there's so much steel in the foundation. But I remember having a specific conversation about the windows, and he's like, and I took a picture of all the rebar around the window, and I was like, and he was like, I've never put this much rebar around a window. And he's like, I put hundreds of windows in, and he stopped, and he goes, and they all crack.
They all crack.
And I laughed, and I was like, I think this is why
it's
there, you know, like to prevent that cracking in the corner. Because that was the impressive thing here. I mean, the foundation's complex, and looking back, like we could have got rid of some corners and worked through that, but we were
to that point of like, it can feel like on residential, especially high-end custom homes, that a foundation's over-designed. But these aren't spec in like residential building code walls. Like if you put engineering numbers to the foundation walls that are in the tables in the residential building code, they don't check.
So what is the like? What
Those
is the
don't
point
pencil
there?
out.
So
you can build an 8-foot wall
with
no reinforcing.
Right.
Like if I apply math to that, it does not work.
Right. So why is it in the code that way?
They call it like a prescriptive building code, right? And I haven't gone back and like studied like all the things that went into it, but they just came up with like, this is how things have always been built. This is what has worked. We are comfortable that this works. So prescriptively, you can continue to do this in residential building. So that's 1 unit, 2 family homes, and then above that's commercial, and we have to own it as engineers.
Got it.
Right? And so that's where, when you have like this house, a high-end custom house, we have a brick facade. Now you put a shelf into a wall, and you have a contractor that sometimes doesn't even put rebar in the wall. Now we have a 6-inch thick stem on a 10-foot tall wall that's extra high.
That has no rebar.
That has no rebar in it. So when we add rebar, and a 6-inch is not a lot of bending for that load, we have to add quite a bit of rebar in to make it work. But it's a huge jump from residential building code, because you're really building a commercial wall.
Could we have built this house like that without rebar?
10-foot tall, you're getting kind of high. I think.
But I mean, not from a structural standpoint. I'm talking about you're saying residential prescriptive code.
Like 8-inch wall, 8-inch thick, continuous height, no rebar by code.
It would have been fine, and we would have passed inspection, and the house would have been fine.
Yep.
When we're building a house like this, or what triggers someone to get an engineer involved when you're dealing with building a single-family residential?
There is some gray area there, right? Sometimes it's up to the town. So if a town inspector says like that house is out of our comfort zone, that's more than a standard house, you need to get an engineer.
Which would be
this, because they'd come here and be like, I don't know if that roof's going to stand up, right? Like, there's no table that says this curved roof with all the levels and roof. You can't, like, that's not a prescriptive design. So you got to hire an engineer to go through that work. Same thing with like large spans, tall walls, like your traditional floor to floor, like your 8-9 foot, they have a stud height for there. They have your typical floor spans. Like the residential building code too is mostly like your old 2x spans, right? Now we have, and why the lumber companies provide engineered floor joists is because they exceed residential building code, so they own that span.
Right.
Same thing for those LVLs, right? Because
so it's
technology has advanced.
Yeah, when you have a lumber company spec out an LVL for you. Yeah, got it.
And then so that's the big difference. And once you get there, and like on a custom house like this, the lateral forces aren't totally there. So if you're doing stuff on, say, the coast, and you have a high wind zone, and you have a lot of glass in tall walls, like that's not prescriptive single-family home design. So they're going to ask you for an engineer.
Got it.
And that's when we get involved. And then where the rub becomes is like, when are we owning an engineering element, and when can you follow the residential building code? Right? There's kind of a balance there.
And in our case, and like we want to build a better home, so that's where it's like we're going to lean on someone like you guys to, hey,
I just built a home, we engineered the thing.
Right. We want this home not just to stand up, but to sustain and not deal. Cracking leads to water issues, to mold issues, and so on and so forth. And similar to, with the roof framing, like you don't want that thing bouncing around.
And the large investment, it's marginal. The investment's marginal. The gap between like cutting corners and doing the bare minimum versus investing and doing it right, like long term.
Some people argue how marginal that might be, but at the end of the day, I think if you factor in the cost of repair and warranty and lawsuits, then yeah, I mean, building it the right way the first time is going to be way cheaper.
Yeah, there's design matters there too, right? Like if you took your standard residential home and put it to the IRC and then put it to an engineered practice, the gap wouldn't be that much difference in cost.
I understand.
Like a lot of the cost that goes into a home like this is how custom it truly is. The vaulted spaces, the roof lines, like that continues to add on that compounded cost.
So why don't we go up?
That's the difference between custom and standard.
Speaking of vaulted, why don't we go up to that living room space where that's our first vaulted area?
This is a kind of a unique wall too. You got to pay attention. Like now this has like a temporary stair, how that's built. This wall is resisting soil on the other side, but doesn't have a floor bracing the top of it. So we had to consider how that's built and what type of reinforcing is in there to make sure that it's stable, whether that stair is there or not. This is like a 12-foot span with nothing bracing the top of it, and it's supporting this big wall that comes on top.
Got it.
Right. So that wall has some extra rebar in it to help with the soil bending in that wall.
From an architectural detail, this is one of my favorite things, is having the stair in the garage, backing up, unloading.
Direct to basement.
No bulkhead needed. And Mike, actually, you turned that into a double door, right?
Oh, it's always been a double door.
Oh, it was?
Yeah.
Oh, I thought it was a smaller door in the beginning.
No. Originally, it was
4 foot or 5 foot?
That way you can get furniture down there.
It's awesome. At least 4 feet clear, so you can get like anything you need.
The extra wide stair.
Yeah.
That's
and
big.
And then being able to like swing through that doorway.
It's good detail.
What about in the garage here, Rens? So I know we went with the traditional truss. That was a choice you had made, really just to have it cut, sitting on site and waiting for us. But when you're looking at something like, you know, a shop-built truss system, is there anything that you're looking for?
What am I looking for here? The primary thing to look for is how is the gable wall built, right? So if we look at that top plate, it's happening at the ceiling level, so we know that it's going to be braced, right? Like if that's vaulted, sometimes you're looking at that end truss and how that's going to get resolved. So we have, it's like 2x struts kind of running across the top of the wood roof trusses. You have 2x's lying on top that are running all the way into the gable, and that's going to act as your brace for that end bay. Because otherwise you have that wind load on that wall, and it's pushing right at the ceiling level or the bottom chord of this truss. So you got to make sure you have some structure there to resolve that. When I'm walking around a house, that's the stuff that I'm looking for. I'm looking for an unbraced wall, so an unconventional space that could have an unbraced wall, because like that kind of thing can get overlooked by a typical framing crew. We have a job right now where that was starting to happen, and it created an eave and a separation at like the eave and the soffit detail outside of the wall, and it was an exterior stair in a renovation. So it got cut in, and then the king stud didn't go all the way up to the attic, so it was completely cut off from the floor to create the stair and not replaced to go full height.
Wow.
But it's an easy thing to miss if it's not something you're used to doing.
Right. Cool.
The other thing I'd look for here, and I doubt that it's a problem here, is like, do we have wall studs underneath the roof trusses? This is a single story roof, so I don't think I'm going to be worried about your typical, that's like, let's say a single sill or a double sill spanning that 16-inch wall stud.
Yeah.
But those are something I'm looking for.
Rens, I'm going to ask you a question that a bunch of people have asked us about.
Okay.
This whole 3-ply header thing. So we replaced our 2 layers of plywood with foam.
Yep.
You're not prepared for this question, but
Okay, let's go for it.
But so we took out the plywood and we add a 1-inch piece of foam, and the reason we do that is just to create adding some additional
it's a great detail.
insulation and thermal bridging.
Do you want to do more and go to 2-ply?
Say it again.
Do you want to add more foam and go to 2-ply?
No, what I had talked about it, and they were like,
Headers and go with more foam.
the thing that came up over and over and over on our videos is like that you ruin the header. You went from now it's a 2-ply because the foam doesn't add any structural integrity. And in my mind, I was like, no, all of the load we're dealing with is vertical. I still have 3 2x10s that are supporting gravity load.
Yep.
So even though there's a piece of foam separating one piece of it, it's still supporting the load it needs to.
Yeah, completely. I'm in agreement with you.
Yeah.
You put the layer of insulation there that's performing as you demand. If somebody's picking on like the technical side of that, like if you're going to do a 3-ply LVL, you have a screw pattern, right? Even in our design drawings, we own that screw pattern, and that's to make sure that they share consistent load and shear. That's like the shear plane between.
And
each
that's
ply.
that's the argument.
And that's the argument they're making here.
Yeah.
But like, what in reality, what's going to happen here, especially on like short header spans, is like it's going to get loaded, and then like it's already being uniformly loaded from the studs above, right? Like it's going to the joists or the jack studs that are coming down those squash blocks, so it's pushing down on all of it. And if one side were to move, the other side's going to engage before that could continue to go down.
Right.
Because it's all locked in.
And anytime we do have a long span, you have a screw pattern on them, and like that the R5 over there, you know, that header still has foam in it, but you see that they got long lag screws or the Fasten Master screws right through the foam, tying everything together.
The screws aren't going to do as much in that case because the plies are separated. So where that person's probably talking about is you lose the shear flow capacity from that screw attachment, because now you're putting the screw in bending because it has that 1/2-inch insulation gap of bending there. Versus when the 2 plies are next, there's no screw bending. It's just like pure shear transfer.
Now, is it at all a concern?
I am not concerned.
Okay. Cool.
There's probably a better technical answer, but
I like iron.
I'm not shaking in my boots.
So one of the things you had pointed out is this blocking. So on the outside we have, I forget what is that strap called? What is the intent with this? Like beyond, like my interpretation is you're basically putting a belt, like I wear a belt on my pants and I'm holding everything together. Is this doing the same thing?
belt on your pants.
Well, you know how like
hold
I don't want my pants to fall down. I put the belt, I tighten it up, and it holds my pants from falling. Is that essentially what? Because this band goes around the whole house. Am I wrong?
The way it's called out is above and below window openings.
Oh, I thought it was the whole house.
So
Finest part of the house without a window.
Oh, true.
So you're
You know?
yeah, that could be the case. So
Yeah.
in houses like this with the custom, you don't really have a lot of interior shear walls that aren't crazy, like punched openings full height to where you can find good interior shear walls. So
We have
we're
one.
forced to use all the exterior walls, which have a bunch of openings. And so what happens when you look at a shear wall with a big opening in it, you can look at it as two separate ways. And this is where my technical stuff falls apart. There's like a segmented shear wall, and then like, I forget what the other term is uniform shear wall. So you can look at it as like a column, a short shear wall there, and a short shear wall here, and look at how those work. But the width and the length of the shear wall really helps you in terms of creating demand. And so that just tells me that we didn't have enough consistently long shear walls to be able to generate the shear value or the overturning. And we had to strap these windows to get the shear, the force transfer to get this to work as one shear wall instead of two separate walls because that opening's so big.
Got it. And as far as shear, we have that one interior wall here. But I think this is one of, we have, say it again?
There's a
I
couple
could
of them. There's this one.
In the hallway.
It goes all the way along the hallway, and then there's one in the primary suite.
Yeah, so at
then
my
there's
house,
basement too,
I have a long wall. My center wall in my house on between level 2 and level 1 it's a 59-foot long, and it has a 4-foot wide opening, 2 4-foot wide openings. Otherwise, it's a completely long wall, and the back of my house is mostly glass. But I did that so I could have one continuous shear wall in the center of my house, and I cantilevered the diaphragm off the back of the house. So I don't have any of this on the back of my house, but I sheathed that interior wall. And so I have a 20-foot diaphragm that's 60 feet long, cantilevering off that center wall.
When you're looking at a 2-story space like this, what are the important factors to consider?
What am I looking at?
Yeah.
I'm looking at this wall. This is where I start to pay attention to, right? Because that's not your traditional stick-built wall. So you got to make sure that we're braced, because what happens is wind blows on that wall, and there's no floor coming in at that normal height of 9-10 feet to push that wind load in, because that's what's going on. Is the wind blows on the studs, and the studs pushes loads to level 2 and level 1, except we took out level 2. So now that framing's got to carry the wind load all the way up to the ceiling. So I'm looking to make sure that that's built correctly. And so right here, that's why these are LVL studs, and they're full height king studs.
Because if you were split, you'd essentially have that hinge.
You would have a hinge right in the middle of the wall, which is where you would normally, like the other way is you could take a beam and flip it horizontally and run this way, but then it's going to be deeper than your wall, so it's not going to have a nice look. Here you'll notice that's probably picking up framing from the other side anyway, so you're a little braced over there, and then this is the full height piece over here. But that's even connecting the full height studs right on that edge.
So that was a fun wall to stand up. That was one of the first ones in this part of the house. Yeah.
You built that flat and stood it up?
They did, yeah. So this room back here, there's a lot of glass, like a lot of glass.
Okay.
And flat roof, so we don't have a lot of insulation value. We'll have to address that.
Is there a roof deck above this?
No roof deck. So something like this where there's punched openings everywhere, even though it's a 1-story, part of the building, what are you looking at in this room?
What am I looking for? I guess I'm looking for the same thing, right? You have full height king studs, because you could very easily make the mistake here on where you go. So those full height go up top. And then you have your headers. And then from a lateral perspective, you'll see some houses, and hopefully we didn't do this here, is you could end up trying to put moment frames on something like this. You're like, I have all this glass. Some residential engineers might not look into cantilever diaphragms. And it's something we do a lot in multifamily. So you have this big long diaphragm back here, and we have this small projection. So rather than like throw all this extra cost out here, we're going to analyze and design this diaphragm and that diaphragm to cantilever out to take on that lateral load from wind and seismic.
Can you explain what diaphragm is?
What we're sitting on right now is a diaphragm, right? So this is your floor sheathing, which is it transfers like us walking around in furniture from joist to joist. But this sheathing is completely, like, it's designed, and the nailing patterns and how it connects to the exterior wall is what takes all of the lateral loads in the building and translates it to those shear wall elements that we want. So a seismic event happens, or wind blows on this house, wind comes from the walls into the second floor, and then this diaphragm acts like a big horizontal beam. And that's spreading that wind load out to all those elements. So that's really what that does. So on this one in particular, where we cantilever off the back of the house, wind's gonna blow on this wall, it's gonna wanna try to bend it this way off the back of the house. But that diaphragm's gonna be designed with the nailing pattern so that that's stiff enough and strong enough to prevent it from twisting.
Got it.
Because that's pulling it back.
And then the same thing is on the floor here, same thing. It's basically, that's why it's anchored down to the foundation and essentially works as like a 3-sided box.
Correct, yeah, I don't know if this is on a foundation
It is
wall
on,
system
yeah,
or
full foundation.
Full foundation, yeah. So like this floor, you don't have to worry about because this is just a part of the big diaphragm, right? Like some of the load's gonna come into this room and go to the foundation walls. This one's cantilevered off the back of the house.
Got it. You wanna go to the primary suite? Well, Mike, why don't you explain like kind of how you guys approached this and how you guys ended up framing it?
We laid out all the trusses over on the ground and snapped the lines to know, the roof pitch, so the doubled up rafters, the collar ties. And so your roof pitch, the higher up one, that was all framed on the ground and everything nailed off, and then swung those into place, and then we just popped in the lower roof pitch after. Full balloon frame on the gable walls, balloon frame on that gable wall, stood those up, connected the walls in between, all the rafters or the trusses were already built, then we just carry them over the wall, drop them in.
And how did you build the ridge board or the ridge beam at the top if you were building these as individual trusses as you went?
There's no structural ridge.
There's no structural ridge? So those are just going nose to nose right now? And then this ceiling in here that we're looking at here is purely to just create the room.
Correct.
Right, it is a sloped ceiling framing.
It's interesting, there's a lot of that in this house where you're creating lower roof pitches, or like in the living room, you have those 4 windows that are designed to look like 4 dormers popping up through the roof. But on the outside, it's different. It's just a roof with 4 windows on the back wall.
Yeah.
And in here, it's, you could have had a super high super high ceiling, but it was too much. So they brought it down, and this is still, a great.
It was important to the exterior design to have the roof line correct, but
and equally as important on the interior to have a shorter roof, so it wasn't so overpowering when you walked in.
To go back to the earlier conversation, that's where like the pricing of a custom home to a traditional home, and like doing things right versus doing the bare minimum to meet code, like starts to get blurry.
Yeah.
Because like you don't run into this type of thing.
There's all the consideration of not only how it gets built, but also, the end result of how the client interacts with it from the outside and from the inside. And those are the things that,
that experience matters.
Right. Let's go upstairs. Where are the challenging areas up here, Mike?
We have ceiling framing. You'll notice the ceiling framing doesn't come down on the top of the wall, right? On both ends of this house, the ceiling framing is up in the roof. So when you actually start to analyze that, old building code used to let you pull that ceiling framing up 1/3 the height of the roof. So like you could do vaulted space under the previous residential building code with no ridge beam. Because what happens in a roof is when you design a house, you put your ceiling ties, hold the walls together, because when snow loads the roof, the roof wants to spread out like this, so that ceiling's holding everything together. When you start to push your ceiling up off the top of wall, that's when you have to start designing and engineering the roof to be stable and not let it spread out, because you're not using that ceiling as a tension tie anymore. Now,
does the pitch of the roof become a factor in like the load capacity?
It does, yeah. Or it impacts the design of the joist, right? Because there's a factor of like your loading based on the pitch of the joist.
Got it.
So that's how.
Yeah. So if the flatter it is, the more weight it's gonna.
Correct.
Theoretically. Yeah.
Yep.
Got it. Yeah, I think
it also gets shorter though.
What?
It also gets shorter. Like the steeper the roof, the further it has to go. Like if your house is 32 feet wide, and it's at a 8 pitch, and then you move it to a 12 pitch, that joist just got an awful lot longer. Even though there's
so it's almost like you're working in benefit and against it at the same time.
Those aren't numbers I have. I haven't run those in like 8 years, so I don't have any.
That's okay.
I don't have a rule of thumb anymore.
Actually, a question I wanted to ask you downstairs. What is your opinion on when the headers get pushed all the way up? And it's something that, I know, I'm not sure if you had directed it or Dimitri had directed it, but pushing them all the way up underneath that top plate versus being right above the window, got some back and forth feedback on it. I've always liked it because then it gives you the opportunity to adjust that door height or or move the window location. But is that
structural performance? There's no difference to me. So but I agree with you. Like pushing that up gives you total flexibility. If you ever need to modify that door height, it's an easy fix.
Yeah, but you can start to see how this LVL. I mean, this is just a complicated section. This whole front, like just the way the LVL lands down on this wall here, down this hallway. But you can see this is like your main pitch of the roof. We can actually see the scabbed on curve piece there.
How you create the curve. Yeah, that's awesome.
And essentially that, you look underneath here, you kind of see how they went from that and then kind of tie it into that exterior wall. So essentially one of the, your design was really to land on here. Like this is your structural.
This is the structural wall, yeah.
And that's just, that's where that.
That's essentially acting like a small dormer.
Right.
It's like a shed dormer.
This right here, super complicated.
When you have such a large roof that's taking on like a very complex geometry, has multiple levels of load coming into it, and you pull the ceiling up from, say, your top of wall, that's a very critical joint. So if you design to, say, service level, like code minimum deflection criteria for a roof, you're probably going to get a lot of excessive cracking at the ceiling joint. Versus like actually designing this roof into like the level of home and the level of detail you're trying to accomplish, right? Like you do not want movement at that joint.
Right. Hence why you have the doubled up.
Like the double 2x10 is going to help limit movement there because it's sistering, sandwiching that joist, right?
But it's funny you say that. Even that joint right there cracking,
so critical.
And you think about in a lot of homes nowadays, you have crown molding, and it gets hidden, not necessarily in this detail, but in similar details. And oftentimes you see the crown molding crack, and then they come in, they caulk it, and they paint it, and it cracks every year. And when the reality is, it's oftentimes that's blamed on the humidity or the temperature that keeping the home, but the reality is like, is your building moving?
Is there movement there?
Right.
Yeah, very well could be. If you have a house or any house that you go in that has like a vaulted family room with a fireplace on the gable end, look up at the ceiling. Look at the drywall around that edge. They used to never put those in with ridge beams. So that whole roof assembly that we were talking about that gets loaded and wants to spread apart, that's the exact scenario you have in like any house built back in the 90s.
This was also a fun one I think you guys had to work on because your framing member had to actually get pretty small for stair clearance.
Yeah. It's down at 2x6. It's like 5.5 inches with the curve.
But from the inside, this is what we're looking at. But on the outside, there's actually multiple like overlays.
Yeah, because this roof line comes down and then flares at the end, and then over here, like this loft roof, that flares out. So then you have this not a perfect hip with two different curves tying into each other.
Complicated joint.
Yeah. Rens, this is actually a great spot to see. Here's you get that rafter. It's landing here on one pitch, and then transferring into a steeper pitch there with that curve.
That's a tough detail to build, gentlemen. Nice work. That is not simple.
What is the thought here, or like what are you looking at from a structural perspective? Like what is the concern? And
the geometry is the hardest part to get down, right? So like nailing this geometry I think this is far more challenging as a builder than it is an engineer. We have two different roof pitches. They might look similar on the outside, and that curve kind of blends them together. So from the untrained eye, they might just look at that as one roof piece, but we really are seeing two different roof planes. So it's critical that you have a load-bearing element at that kind of break of those two different planes, because that load path, we'd never be able to take this vertical load path and then kick it that way.
Right, because you'd essentially have a hinge, and it's like, what's ever going to prevent that?
Exactly,
hinge?
It's the hinge.
In a situation like this, say if the LVL existed, say there was 48-inch LVLs, and we could cut that.
Oh, for sure.
Would we be able to prevent something like a load-bearing wall, or are we just preventing the need for two materials?
Yeah, you can design anything. It just takes space and money, right? So that's how I always like to respond to that. You hypothetically could model that as one continual element for sure. It would act like a curved beam, right?
Yeah.
So
and it would work I think I'm asking the same question, but would it work better or just different?
I would say different.
Yeah.
Better, like you would design so that it performed to what it was required to do, right? So you could undersize the curve beam, we could undersize this, like if this went to a beam that was undersized on the next floor, then our roof isn't gonna perform like we wanted it to because we undersized something. So if we're designing to its performance capacity, it should perform the same, just different. And to your point, like that's what you're seeing in the mass timber world, like this big push and this big movement of mass timber, which is an engine coming.
Yeah.
There's a lot of custom design beam where they're like custom making these rolled geometries. You'll see this with like Sperry tents or high-end tents companies, right? Like they're doing curved laminated pieces.
Yeah. Similar to what we see in the attic where this comes down, lands on a beam, right, Mike?
Yeah.
These?
Yeah, you can see the LVL sticking up through the floor.
So this roof line, they're the same curve. I'm just wondering if the exterior wall's in the same relevance to like this spot to here is closer than this spot to there, right? Because that must be like a bump out for some kind of front feature. So here it's essentially the same types of flare. It's just a different geometry. So this bearing line comes in much closer to the exterior wall, and so that like it's almost like you just create a gusset instead of that totally separate bearing line.
So essentially that beam is doing the same thing as this wall over here.
Yeah, right. Like that service spot is right here on this side, and then that flare happens to the outside.
Got it. Let's hop up in the attic. And when I looked up here, I'm thinking that this is our roof, but it's not. It's the lower section of the curve.
Yep.
And then if you look through that, and that's that.
Yeah, because this is a 9 pitch and then it goes up to a 17.
It's a 17 pitch.
Yeah.
Oh shit. That must have been kind of cool to build. Those are like angles you haven't cut before.
Right.
Yeah, you
So just so
You're like,
and
my
let's
square
just-
doesn't go that far.
We'll watch our step here. But it's like looking at this. I mean, there's so much going on.
Yeah, there's nothing simple about this roof.
I gotta give credit to Dimitri and the guys at ChevCon. In this whole design, they worked, obviously you guys were working through the design with them. They added these 2x4s. I'd asked him about them, like, oh, he's like, these weren't on the drawing, but I added them because if you ever get deflection, I don't want your ceiling to crack.
Yeah, it's a nice detail.
But so looking at this is one of the biggest things that people are like, oh, this roof's overbuilt, it's complicated. What makes you say that it's built appropriately?
If you think about a traditional roof that people are used to seeing, you're seeing that colonial house, 28, 32 foot wide. It's a standard A-frame. Mm-hmm. They might have a dormer or two on it, but you're generally talking like pretty generic framing. Like that is very predictable on how that's going to perform. There is so many different roof lines. We were just talking about a 17 pitch, a 12 pitch. What else we got?
A 9.
12 on the garage is 17. These dormers are at 9. But then there's front's also 17.
Yeah.
But then all the different radiuses that are thrown throughout. Every section is different. Like this section over here is 48 foot 11.
Yeah.
This section over here goes down like 43 feet. That front dormer over there is 21 foot 7. This one over here is 21 foot. So it's like
exactly. And just look at all the different pitches and all the different roof planes. There's as many on this house as you'll see in any custom house. And what happens is things perform differently. Like the reason we have a roof beam framing through an attic into another roof plane with an overbuilt roof. There's all different types of load paths going on, and you have to look at it several different ways. So we have finite element models of these roofs to understand how they perform. Are they performing the way that you want them to perform? And again, it comes down to performance and serviceability. Could something be lighter because the piece of wood has the capacity to support the load? Maybe, but you might have more differential movement at your ceiling joint when you don't want it, right? So all of those things come into play when you're designing this type of house, and that's how you end up with a really beautiful home. Like when you brought this home to me the first time and I look at it, I'm like, yeah, it's a nice custom house. We do custom houses.
Yeah.
This roof is the most complicated custom house we've done so far.
I'll take that.
Till the next one.
But just walking around, so you make sure that we did our job correctly. Mm-hmm. And we've talked a lot about a lot of the details and like the things that you look for, and we pointed out some of the things some of the things that you're going to check back at the office, some of the things that we'll double check here on site. But, you know, overall, what is your take on the way that this has been executed?
You guys are a top-notch framing crew. Like, this place is built extremely well. You follow the details. You're above and beyond like your bare minimum code spec, right? Like, we're designing to performance, we're designing high quality. You get, like, the edge blocking is the perfect detail, right? It's such a lot of people ignore a gable wall and how that wall pushes on the floor of a building. They don't put blocking in on that gable wall. And to see a team like you guys put that level of effort in and that attention to detail, it gives you a level of comfort that you're detailed, you're detailed, right? That's the most important. Like, if people aren't paying attention to detail and they're just getting a frame together so that they can go to the next job, that's like that to me is perceived risk. And so when I see people that are pay attention to detail, I know that they're doing things right.
Appreciate it.